So welcome again in the VLSI technology lecture. So in the last lecture, we were discussing about the Fick's law of diffusion. So we were on this particular slide. So we have already discussed about the Fick's first law of diffusion, in which we have seen that the dopant flux that can be given as minus d dou c x comma t divided by dou x. Okay, where J is our dopant flux, which is nothing but the number of dopants which are crossing per unit area per second. So now we have to look at the Fick's second law of diffusion. So we can see in the in case of the Fick's second law of diffusion, we can take a certain specimen of a semiconductor piece, okay, which is in which we can consider two different planes at a certain places. Okay, so let us say we are having one plane at this point and another plane at this point, and what we can say that is these two planes are separated by a distance of dx, and its cross sectional area is uniform. Okay, so that cross sectional area is equals to a. So now we can see in this case that under this particular plane, okay, so the dopant flux is equals to j1. Okay, so at the j1 rate, the number of impurities are actually coming to this particular plane, that is your entering flux. Okay, so this is your entering flux. Similarly, the flux which is coming out of this plane is j2, right? So what we can have is we can write this as like if j2 and j1 are not same, okay, then we can write the net accumulation of the impurity atoms within this incremental volume. Okay, we can have the volume, so that volume will be equals to, obviously, this cross sectional area is a and this distance is dx, so we can have this incremental volume equals to a into dx. So now if we wish to write this equation, if this fluxes are not the same, okay, if J1 and J2 are not the same, then there will be a certain net accumulation within this incremental volume. So first of all, we can write like J2 minus J1 divided by dx. So that can be equals to dou J upon dou x. Okay, simply where J is function of both space and time. So we can write this equation as dou J upon dou x. So now let us say that if we suppose we want to calculate the number of impurity atoms which is going to increase within this incremental volume, okay, per unit time. Okay, so what is the rate by which the impurity atoms are actually increasing? Okay, so that we have to look at due to diffusion, obviously due to diffusion. So we have to look at, because the diffusion rate outflux of this diffusion, or the diffusing dopant atoms are different at this particular plane and this particular plane. Therefore, there will be a net accumulation of the dopant atoms at this point. So if we want to calculate the number of impurity atoms which is going to accumulate within this volume per unit time, then that can be calculated as by writing this equation dn upon dt. Okay, so this will be giving you the number of n is the number of impurities. Okay, so it is number of impurities per unit time. So that can be calculated by obviously if we write what is the rate of change of concentration of impurity atoms within this particular volume. Okay, so as we know that the concentration, we are actually denoting it by c. Okay, c x comma t, because it is both the function of space and time, so it will be denoted by c. So we can write the rate of change of concentration, we can write it as a dou c upon dou t. Okay, obviously I have not written here x comma t, but it is obviously a function of x and t. So if we have this dou c upon dou t, then if we multiply, so you can note it down, what is this unit? This unit will be number of atoms per unit volume per unit time. Okay, so if you multiply this particular function with the net volume a into dx of this particular incremental volume, then this volume will be cancelled out and you will be getting the number of impurities per unit time. Okay, this is the desired result. Similarly, again, we can calculate the same thing. Okay, we wish to calculate the same thing. We can also calculate it by calculating this J2 minus J1. Okay, so this J2 is nothing but your output flux. Okay, and this was your input flux. Okay, so J2 minus J1. So as I have already defined you, what is the unit for J2? So J2 is nothing but it is the number of dopants crossing per unit area per second. Okay, so once you will multiply it with the area, okay, because J2 is smaller than the J1. So when you subtract this quantity J2 minus J1, then this net result will be a negative value. Okay. So this negative and negative terms will be cancelled out, or you can say it will become positive. So if you calculate J2 minus J1, okay, obviously it will be giving you certain rate of dopant that is crossing per unit area per second. Okay, so I mean the change of dopant, number of dopants which are crossing per unit area per second, and if you multiply it with the area, you will be getting the rate of net change of your number of impurity per second. Okay, per second. So whatever you are calculating by this equation, the same thing you can be calculating by having this particular equation. So now what we can do is we can particularly we can write J2 minus J1 upon dx. You can write here, okay, dx and ds you can multiply. Okay, so we can multiply with the dx, we can divide it by the dx, and later on this J2 minus J1 upon dx can be replaced by dou j upon dou x. So that can be written as dou j upon dou x. So we are getting this particular equation, okay, of rate of change of number of impurities within an incremental volume. Okay, so how this impurities are going to change within this particular incremental volume. So now from this equation itself, what we can have is we can equate this term equals to this term. Okay, and therefore you can see that a dx will be cancelled out, and we can have an equation that is reflecting you dou c x comma t upon dou t equals to dou j upon dou x. So basically here it is denoting the change of concentration both in space and time. Okay, space and time, because here it is changing with the time, and here you can see the equation which is changing with respect to x. Okay, so basically what we are going to get is we are going to get this particular equation which is dou c x comma t upon dou t equals to minus dou j upon dou x. Now we have the equation for j from the diffusion first law. Okay, our Fick's first law of diffusion. Okay, so that equation we can substitute like j equals to minus d dou c upon dou x. So if you substitute that one, we can negative negative will become positive, so that dou upon dou x, and then we can substitute for the j. That equals to d into dou c upon dou x. So now we have arrived to a very important result. Okay, because our dou c x comma t upon dou t is given by this particular equation. Now based on the like how this d will be considered, okay, based on the uh, d, okay, whether it is a constant or it is a function of doping concentration, or it is a variable quantity, I mean to say. So whether it is a constant or it is a variable, okay, this equation can be transformed into a different equations. Okay, so first of all, as we already seen experimentally that d can be a constant or it can be a variable. So it is actually depending on the various conditions, situations. Okay, so in some situations d can be treated as a constant, and in some other conditions d can be considered as a function of space and time, or it is a function of basically concentration of the impurities. So we will be considering the very first case in which d is constant, and most probably we are using this one. Okay, so first we will be considering if d is a constant. In that case, obviously d will come out of this particular differential equation, and we will be getting this equation dou c x comma t upon dou t, which is equals to d dou square c x comma t upon dou x square. So now we have to solve this particular equation, okay, to get the doping profile of your diffusion. Okay, so because if we solve this particular equation, okay, we can get the doping profile. Okay, So how our doping profile will look like, what will be the mathematical equation that will govern this particular diffusion process. So now we can see that we are having one diffusion constant d. So normally d is further defined as d equals to d naught and e to the power minus ea upon kt. So where ea is our activation energy and d naught is generally a temperature independent diffusion coefficient. So generally what happens is d is itself depending on the value of a, and it is a temperature dependent parameter. So we can see that generally for the substitutional impurities, whatever we have defined so far, okay. So for the case of substitutional impurities, because in the case of substitutional impurities, you can recall that we need to, while making a movement of a particular like impurity atom, okay, if it is, it wants to make a movement, that time we need to break certain bonds. Okay, we need to break certain bonds, and then again we have to form a certain bonds. So generally it requires more energy. Its activation energy is larger than as compared to the interstitial impurities. Okay, it is experimentally found, and therefore it is having that the diffusion constant for your substitutional impurities are normally very small, okay, and cannot diffuse very fast. Okay, cannot diffuse very fast because it requires really lots of energy. Okay, so energy is required is much more in case of your substitutional impurities, and therefore your interstitial impurities are actually moving very fast because of having a higher value of the diffusion coefficient. Fine. So now we have to basically look at the this equation number 3. Okay, we have to look at the equation number 3, and we have to get a doping profile. Okay, when we are going for the diffusion process, then we have to go for the doping profile. Okay, so how the profile will be if we going for the diffusion process. So basically the diffusion process itself is actually divided into two different parts. Okay, so the first part in which you can consider this picture, which is our first case. In the first case we can have the infinite source condition. Okay, infinite source condition, or we can say it is a constant source condition. Okay, so in this case what we have is try to understand from this picture is so basically what we do is we are actually placing our silicon wafers in our diffusion furnace. Okay, so after placing it, obviously to diffuse a certain impurities, we need to have certain source material. Okay, from that source material we have to send our impurity atoms towards this particular chamber. Okay, when we want to start the diffusion process. So initially what we do is we have to keep on supplying the all impurities, okay, which we want to diffuse into this particular diffusion uh, furnace. Okay, so in the infinite source condition or a constant source condition, we mean to say that while doing the initial diffusion process, we need to keep on supply all the impurities. Okay, we have to apply, we have to keep on supply the impurity atoms. Okay, impurity atoms will be always present in the ambient. Okay, we have the particular wafers, and this wafers will always be surrounded by the impurity atoms. Okay, it will always be surrounded by the impurity atoms. So whenever, let us say, this particular window, it is surrounded by the impurity atoms, obviously a certain amount of impurity is going to be actually diffused through this particular layer. Okay, as we see that this is our SiO2 layer, and this SiO2 layer uh, is actually acting as a mask for the case of the dopant atoms. So here this impurities cannot penetrate, but those areas which are opened, okay, these are the exposed silicon wafers. Okay, this is the exposed silicon area. So this, from this area our atoms can diffuse. So what we are doing is, in the infinite source condition, we are keep on maintaining the supply of our impurity atoms. Okay, it will be keep on sent. Okay, so now these impurities will start initially start diffusing. Okay, so when it will start diffusing, the thing is that because we are maintaining the supply of the impurity atoms, okay, the concentration of the impurity at the top of this surface never changes. Okay, it never changes, it never goes down. Okay, it never goes down. And basically whenever you see what will be the maximum, what will be the means concentration of impurity atoms, if we want to plot the profile, you will find that the maximum concentration of the impurity atoms will be at the top, at the surface. Okay, at the surface it will be maximum, and that maximum value will be actually given by the solid solubility of this particular dopant atoms into your silicon. Okay, so that maximum value is actually equals to Cs. Okay, and that is called as your solid solubility. Okay, so it is basically maximum limit which is available at the surface is solid solubility. So its concentration cannot be greater than the Cs. Okay, so that will be equals to a solid solubility. Fine. So what we are doing is we are giving a certain temperature of the furnace, and then we keep on sending the impurity atoms. Okay, so this impurity concentration can be actually maintained. Okay, can be actually maintained. Okay, so it will be available. This particular impurities will be keep on available. Okay, it is keep on coming. Okay, keep on coming, and therefore we are saying that it is an infinite source condition or a constant source condition. Okay, so source is actually always on condition. It is always on. We are keep on supplying the impurity atoms. So initially it will be diffused. Okay, initially it will diffuse up to a certain depth. Okay, so after having the initial diffusion, okay, generally what we do is actually this is the most practical way of doing the diffusion. In the case of diffusion, initially we have to send the impurity supply. Okay, we have to make the impurity supply on, and then this impurity atoms will be keep on coming. Initially we have to do the diffusion, and after some time we have to shut off this particular supply. Okay, we have to shut off this particular supply, so this valve will be actually closed. Okay, so we will not be sending further impurities. Whatever impurities are actually means absorbed or diffused to this particular layer, you can see by the dash this red line, red area. Okay, so basically whatever the diffused atoms which are available in this particular red zone, when we further heat the wafers, okay, after shutting off this particular supply of the impurity atoms, then these atoms are going to further diffuse into your wafer. Okay, it will further diffuse. Okay, only these amount of atoms. Okay? So there will be no supply of the impurity atoms afterwards. Okay, so this initial step in which we have maintained the supply of the diffusant atoms. Okay, that is called as the pre-deposition. Okay, pre-deposition step. After performing the pre-deposition step for a certain amount of time, we have to turn off the supply of our impurity atoms, and then further we have to raise the temperature of the wafer so that the already diffused atoms at up to this particular area can be further diffused deep inside your substrate. It will further diffuse deep inside your substrate. And generally this second step is called as the drive-in step. Okay, drive-in step. So we can understand from this picture is that whatever with the amount of total amount of impurity that has got diffused while the pre-deposition step, after driving step again the total amount will remain the same. Total amount will remain the same. The only thing is that here the profile will be, it is having very large concentration of the doped impurities, and after performing the driving step, this concentration will become less because it will be diffused further into the material. Okay, so it will go deep inside the material. So total amount of impurity will remain constant, but the concentration is going to be changed. Okay, so concentration of the impurity will change. Fine. So what we are saying is, in the first case, infinite source condition, we are saying that in this case, the source of impurity is always on. Okay, source of impurity is always on during the diffusion, and this particular process is called as the pre-deposition. Okay. And the second thing that we have said is that the surface concentration of the impurity is a constant. Okay, this surface concentration, okay, on the top of this, the surface concentration will be a constant, and it is actually limited by the solid solubility of the impurity atoms in the silicon. Okay, that will be the maximum means diffusion that may be possible at that time. Okay, that may be available in the gaseous form, and then later on it will be diffused into the solid. Okay, so that is your solid solubility. So that concentration is governed by the solid solubility, so that will be equals to Cs. So now what we can do, just keeping this picture in mind, first of all we have to divide this. As I said that this diffusion process is actually divided into two different cases. The first one is, either you can say it is a pre-deposition case, and the second one is called as the driving step. Okay, so in the case of pre-deposition, we are having this particular case. Okay, so while dividing it into this two part, we can see that if we solve it for the pre-deposition case, what we can have is, we can have the certain boundary conditions. Okay, certain boundary conditions and certain initial conditions. So that boundary condition and initial condition, if we keep these boundary condition and initial condition into equation number 3, then we can get a particular solution for your doping profile. Okay, so what are the boundary conditions that we can have? You can see from this picture itself is, on the top of that you can see that if we want to write C x comma t, okay, if we want to write at x equals to 0, then at that time what will be the surface concentration? That will be equals to your Cs. Okay, so we can write certain boundary conditions. Okay, so that boundary conditions is C at x comma t. So x equals to 0 means it is at the top of the surface. Okay, so at C 0 comma t, the concentration will be equals to Cs. Obviously at C infinity comma t, at very large distance, okay, the concentration will go down to 0. Okay, so it will become 0. Similarly, at the initial condition, if you see, so at C x comma t, so when t equals to 0, that means that when the diffusion process have not been started. Okay, t equals to 0, when it is not started, obviously at any point within the substrate, the concentration of the dopant will be equals to 0. So what we have to do is, we have to substitute this boundary condition into the equation number 3. We have to solve the equation, and we can show that the result will be something like this. Okay, our result that we are going to get is C x comma t. That will be equals to Cs. It is complementary error function x upon 2 root dt for all t greater than 0. Okay, so this will be the equation, and or you can say it is the doping profile of our dopant material. Okay, after the pre-deposition step. So this is our Cs, which is our solid solubility. Okay, it is based on the solubility or the surface concentration, you can say. So now we can calculate the total amount of impurity, or you can say that what will be the dose. Okay, what is the total amount of impurity, or what is the total dose that we have incorporated into our substrate. So if we want to calculate the total amount of impurity, then we need to integrate this particular concentration of the impurity from 0 to infinity. Okay, by imitating it dx. Okay, so just we are considering it to be a one-dimensional diffusion. Okay, when it is three-dimensional, obviously when it is a three-dimensional diffusion, then obviously we have to diffuse, means we have to go for the limit 0 to infinity for all x, y, and t. Okay, but here we are considering just one-dimensional diffusion. Okay, so that total amount of impurity can be calculated as qtt, and that will be from 0 to infinity C x comma t dx. And where qt, if you do this one, okay, after substituting this value to this particular equation, then this qtt, you can evaluate this one, you will get this value equals to 2 upon root pi C 0 comma t. 0 comma t is same as your concentration of your impurity at the surface, that will be equals to Cs. Okay, root over dt. This dt is the root over dt is a very important parameter, which is called as the characteristic diffusion length. Okay, its unit will be of length, so that is called as the characteristics diffusion length, root d into t. Fine. So after having this infinite source condition or constant source condition, we can again look at the second case. In the second case, what we have is we are having the driving step. Okay. So what we have said, the constant, this particular case too is also called as the constant impurity dose condition or driving diffusion. Okay. So what we mean to say the constant impurity dose condition. So what we said after the uh, pre-deposition step, okay, once we have performed the pre-deposition step, after doing this pre-deposition, what we can see is we have to shut off the supply of our impurity atoms. So the ambient of this particular substrate is actually not having any impurity atoms. Okay, it doesn't contain any impurity atoms. So this ambient doesn't contain any impurity atoms. Okay, so whatever the impurities which have got diffused during the pre-deposition, okay, so let us say it is diffused up to this depth, okay, a very small depth. Okay, indeed, it is a very small depth. It is generally less than 1 micrometer. So this diffusion depth is very small. Okay, so initially it is all the impurity atoms are actually available just near the surface. Okay, it is just near the surface. It is available. Now, uh, now we have to turn off the uh, supply of our impurity. Okay, and then we have to further heat our substrate. So after heating the substrate further, these all impurity atoms which is actually available near the surface, now it will further diffuse. Okay, it will further diffuse and it will go deep into our substrate. Okay, so normally what happens is if we consider the pre-deposition condition and the condition after the driving step, what we can see is the depth of diffusion in case of pre-deposition is very small as compared to the depth of uh, diffusion that we obtain after the driving step. So you can see that the depth of diffusion after driving is this much. Okay, this much. And depth of diffusion after pre-deposition step is only this much. Okay, so normally this width is or this depth is very small. Okay, so normally what we say that this depth profile is generally we are taking it to be a like approximately as a delta function. Okay, we consider it to be as a delta function. Okay, we consider this as a delta function. Okay, a very abrupt change near the junction. Okay, near the surface, sorry, so near the surface, and after that it will become zero. Okay, so we can consider its profile to be a very like a delta function. Okay, so now after having this one, we can further write a certain boundary conditions for the case of driving step, and then we can solve the equation number 3 again by substituting those boundary conditions and initial condition to get the another solution. Okay, after the driving step. So what we can see is, first of all, we are saying it is a constant impurity dose condition. So whatever the impurities that has already got, okay, already diffused, okay, now the same amount of impurity or the same impurity is going to further diffuse. Okay, there will be no further supply of the impurity. Okay, that you have to keep in mind. So what we are saying, this particular constant impurity dose condition can be written by this equation. Okay, so what we are saying, 0 to infinity Cx comma t dq, that will be equals to total dose of the impurity. Okay, whatever we have calculated over here. Okay, so it will be equals to a constant. Okay, it is not going to change. It is not going to change. So it will be a constant thing. And the same thing, whether it is you are having a cx comma t given by this particular equation, and we are integrating it over from this place to this place. Okay, whether the diffused atom is up to this point or after driving a step up to this point. Okay, this integration is going to give you the total number of impurity atoms, and that will be a constant, whether it is a pre-deposition step or it is a drive-in step. Okay, it is not going to change. The total amount of impurity, the total dose is not going to change. Okay, so that you have to keep in mind what we mean to say that the constant impurity dose condition. Okay, we are not further giving the any supply of the impurity. Okay, that supply is now shut off. It is turned off now. So only this amount of impurity is going to further diffuse. Fine. So So basically we are considering the pre-deposition depth profile is generally considered as a initial doping profile as approximated as a delta function. Okay, so based on that delta function, we can write a certain boundary conditions. Okay, so if you like take the first boundary conditions, so at x equals to 0, it will be a constant. Okay, it will be a constant, and if you say it is a differential value, it will be 0. Okay, at any infinity value, again this value is equals to 0, obviously, and the initial conditions that we can have is c x comma 0 is equals to 0. Okay, whenever x is not equals to 0. Okay, these are the certain initial conditions, because we are considering the initial looping profile as a delta function. Okay, so when x equals to 0, obviously the profile will not be equals to 0. Okay, it will be equals to either solid solubility cs, or we can give it by the total concentration. Okay, so that cannot be 0. Okay, so after substituting these boundary conditions, if we substitute these boundary conditions, okay, into equation number 3, again we can solve this equation like the way we can solve for this particular solution. Okay, so we have got the complementary error function. Similarly, if we substitute these boundary conditions, then we can get another equation, which is our that will be our Gaussian function. Okay, so that solution you can show it to be cx comma t, which is equals to qt upon root over pi dt and e to the power minus x square upon 4 dt for t greater than 0. So that will be the equation. Okay, and then we can see that what is the initial value of the concentration. Okay, you can substitute x equals to 0 in this particular equation. You will be getting c 0 comma t equals to qt upon root over pi dt. Okay, so cs equals to c 0 comma t equals to qt upon root over pi dt. So this way we can calculate the doping profile of our diffused atoms. Okay, in this in the two different cases, like for the first in pre-deposition case, and the second one is the after the driving diffusion case. Okay, so these are the two different profiles. Now we can see one thing is that generally uh, the driving diffusion time. Okay, the driving diffusion time is normally much greater than the pre-deposition time. Okay, so pre-deposition is generally done for a very small amount of time. Okay, very small amount of time, and the pre-deposition is actually done for a larger amount of time to diffuse the your impurity atoms up to a very large depth. Okay, so large depth. To increase the depth of your diffusion, we have to go for the driving process, and that process has to be done for a large amount of time as compared to your pre-deposition process. So what we can have is basically root d into t, which we have defined as the characteristics diffusion length. So we can say that generally root dt pre-deposition is much smaller than the root dt driving step, because obviously in this case we have considered these to be as a constant, and because the driving step is performed for much longer duration as compared to your pre-deposition step, therefore this particular equation is always valid. Okay, uh, compared to when we compare with the pre-deposition time and driving steps. Now we can have this particular graph. Okay, you can see this graph I have taken from the Campbell book, Stephen Campbell. So this particular graph you can see here, we have taken the concentration, or you can say it is the doping profile of our dopant. Okay, after doing the diffusion process. So as I said that the diffusion can be considered in two different parts. The first one is the pre-deposition, and the second one is the like our driving steps. So you can see the first one, it is pre-diffusion, pre-deposition process. Okay, so in the pre-deposition process, what we have said, we are having the constant source supply. Okay, we are having a constant source supply, and what we have said, we have said that the surface concentration is not going to change, and it will be equals to the surface solid solubility of your impurity atoms into the silicon. Okay, so it is not going to change. Okay, it is always be equals to your cs. Okay, the surface concentration is never changes. Okay, it won't be depending on the duration of your pre-deposition. Fine, so you can see here in this particular picture, so we are having the concentration. Okay, surface concentration, so concentration of your impurities, okay, and this is the depth, okay. So we can consider this to be as a surface of your wafer, okay. So x equals to 0 means it is the top of your wafer, it is the surface, okay. At the surface we are having the maximum concentration, okay, we are having the maximum concentration of our uh, impurity. And then as we move inside your material, okay, inside your material, this particular concentration will start reducing. It is reducing, okay. It is reducing now, and up to a certain time it will be reaching to a certain concentration, okay. Up to a certain depth for a certain time it will reach up to a certain depth and certain concentration, okay. But you can see these three graphs are corresponding to different amount of time t, okay. As you say, d is a constant, so root d into t is 0.15 micrometer, zero point 0.2 and 0.25 micrometer. So it means that we are actually having three different values of the pre-deposition time. So as we increase the deposition time, pre-deposition time, then the graph is changing a little bit, okay. It can go further deep inside the material if we increase the pre-deposition time. If we further increase the pre-deposition time, this will further diffuse and it will go to a little more depth into your material. But the one thing that we have to understand, that this particular surface concentration in all the three cases, even we are changing the diffusion pre-deposition time, the surface concentration is not going to change, okay. This is one of the important concept that we have to understand in the case of pre-deposition, because we are keep on supplying the diffusion material, okay. Impurity atoms are keep on present, or it is already available, it is already available in the ambient. So whenever it is diffusing, the supply is already maintained, okay. So whatever be the impurities which are diffused into your material, the surface concentration is not going to reduce, because again the materials are actually diffused to your onto the surface, okay. It will come from the ambient, because supply is already maintained, it is already on, okay, it is always on condition. So this is not reduced, okay. At the second hand, in the other hand, you can see the second case, basically you can see here that it is a drive-in step or drive-in diffusion process, okay. So in this case what we can see is basically this uh, source is now shut off, okay, it is turned off, so no supply is maintained further, fine. So when the supply is not maintained further, in that case what happens is, whatever be the source, whatever be the total dose, okay, that total dose will be a constant, okay. So now when we perform the drive-in step, okay, you can see this first curve, okay, for a certain amount of time, okay. In the first curve we have got, okay, we have got a certain concentration of your surface concentration of your dopant material. And after increasing the drive-in step, okay, you can see in the second curve, okay. So you can see in the second curve, this surface concentration is also reducing, okay. This surface concentration is also again reducing, because we know that there is no supply of the dopant material, okay, in the driving stage, okay, because it is a constant dose condition, okay, it is a constant dose condition. So there is no supply is maintained for the impurity atoms. And further, when we increase the driving step time, then you can see the third curve, okay, it is going like this and then it is going up to this point, okay. So this surface concentration is slowly reducing, okay. So that you have to understand the difference between the pre-deposition and the drive-in step. So this profile we are going to obtain finally, okay. It will completely depending on the what is the duration of the driving step, okay. If driving step is performed for a longer duration of time, the depth of the penetration depth will be more, okay. And accordingly our surface concentration of the impurity will start reducing, okay. It will keep on reducing, and it will depend on what is the total diffusion time, okay. So now we can see from this graphs. Okay, now we can calculate the junction depth. Okay, what is the junction depth after the drive-in diffusion, or what is the junction depth after the pre-deposition? Okay, so junction depth we can calculate. Okay, so as I explained you about the junction depth, so generally what we have is, generally suppose that we want to do the doping of n-type dopant. Okay, so n-type dopant, so generally we take a certain substrate which is already doped. Okay, so let us say we are having a substrate which is p type doped. Okay, it is a p type substrate. Okay, it is already having, it is containing the p type impurities, and then we are going for the n type diffusion. So at a certain depth within the material, you will find that the concentration of n type and p type will become same. Okay, it will become equal. Okay, so that particular point within the material is actually called as the junction. Okay, and that junction depth we can calculate by having, let us say, at x equals to xj somewhere, the concentration of the impurity is equals to your cb is nothing but your background concentration. Okay, background concentration, what we mean to say background concentration, this background concentration is nothing but the concentration of your substrate. Okay, it is already p type doped. Okay, so let us say at x equals to something somewhere at xj. Okay, let us say the concentration of the n-type dopant is equals to the background doping, which is equals to Cb. Okay, so if we got this particular, if we substitute this particular equation, okay, into our equation of your dopant profile, okay, just to try to substitute that one, okay, at x equals to xj, your cxj comma t equals to cb into the profile of your dopant profile, okay, that we have got. Okay, the after driving step, so it is actually for the driving step. So driving step we have already got this result like this. Okay, so in this equation, if we substitute x equals to xj, and you can substitute, you replace this particular value equals to cb. Okay, so now this cb is actually multiplied with the root pi dt. Okay, then qt can go to the bottom. Okay, then we can take the logarithm. Okay, if you take the log, then you can have the, here it is log and it is minus sign, so you can change the denominator and the numerator, so it will become like qt upon cb root pi dt ln, and then this 4 dt is going to be multiplied, then this x square will be going to the root. Okay, so this is how we can calculate the junction depth. Okay, similarly we can calculate the junction depth after the pre-deposition. Okay, so after the a similar exercise you can make, and you can calculate the junction depth after the pre-deposition. So that xj will be equals to root 2 root over dt, and it is like inverse complementary error function. Okay, so that will be your cb upon cs, and this way we can calculate the junction depth after the pre-deposition. So I hope this discussion must be clear. We will be discussing about the ion implantation in the our next lecture. So thank you for watching. For any doubts, you can comment me in the chat box. Okay, so thank you for watching.